Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Habib Dagher in August 2022. Habib is, in Maine's engineering and science circles, nothing short of legendary. He founded the University of Maine Advanced Structures and Composites Center, and his accolades and accomplishments since then are far too many to list here. I've been fortunate to know Habib for years. We actually worked on a few projects together in the early 2010s when I was at the Margaret Chase Smith Policy Center at UMaine. And I think I've learned something and been inspired every single time our paths have crossed. Habib and I talked about quite a few different areas that he and his team are working on. Offshore wind, innovative ideas to address the housing crisis, and we could have talked for hours more. Habib continues to do cool, interesting work for Maine and beyond, and I'm glad we were able to capture just some of it in our conversation. Habib, welcome to the Maine Science Podcast. I am delighted to have you here.
Great to be with you, Kate.
You and I have known each other for a really long time. I've been trying to figure this out. I think it's the better part of 10 years now, back when I was working at UMaine. And I'm not telling any secrets here by saying I'm a big fan of what you do. But as I was getting ready to talk to you, I realized I have no idea where you grew up and how you got into science and engineering. If you could just give a little sliver of how you got intrigued by composites and engineering and how you made your way to the University of Maine, because I know, like me, you weren't born here, but you were fortunate enough to get here. And then once we have that background done, I'll make you talk about what it is exactly you're doing.
So sounds good, Kate. And again, great to be with you on the podcast. I would say the feeling is mutual about all the great work you're doing, Kate, here in the state of Maine. So I came to the US as a teenager, about 17 years old, with one suitcase. And I escaped essentially a civil war in Lebanon. And my dad at the time said, why don't you go to the US and do one semester there at college, and then you can come back when this all goes away. And of course, it didn't go away for close to 15 years later. So I find myself certainly very fortunate to have had an opportunity to have an education here in the US. I went to the University of Wisconsin-Madison and got 2 masters and a PhD. And the most important degree of all was my wedding certificate. So basically, my wife and I met at the University of Wisconsin-Madison when I was getting my master's and PhD, and that's the best degree I've got from the University of Wisconsin-Madison is a wedding certificate. So when jobs came and opportunities, I had to go in different places. My wife said, let's go to Maine because Maine's like Wisconsin. It's got snow in the winter and it's got, I love the water. I want to go to Maine. And we thought we'd be here for a couple of years, and here we are.
How is the adjustment from Lebanon to Wisconsin environmentally? That is a big leap.
From an environmental perspective, actually, certainly it's colder, but I grew up in the mountains in Lebanon, and then we had snow every winter and skiing and so on and so forth. So it wasn't very different from that perspective. And the community I grew up in is a Western-looking community. In Lebanon is about 50% Christians and 50% Muslim at the time. And so I grew up within a community that has a lot of very similar Western values. So when I came in, it wasn't a big adjustment for me. I went to schools and French-speaking schools, actually. So not much of an adjustment for me. Of course, the big adjustment is leaving your family behind and as a young person. And that was hard. And not knowing when you're going to be able to go back because the war didn't seem to be ending. So that was hard. But I was fortunate to have met some wonderful people when I was in Wisconsin. And prior to that, I was in Ohio for 2 years as well. I got my undergraduate in Ohio. That's where I came first. And was able to finish my degree in 2.5 years. My undergraduate in Ohio, went to Wisconsin for my graduate programs. And then met some wonderful people in both places and really fell in love with the culture and with the people. And Maine's home for me for close to 36 years now. And I'm hoping for 36 more.
So did you know when you came over you wanted to do engineering, or were you kind of really open to, let's just see what I can find out?
I was definitely wanted to go to engineering at the time. And when I grew up, I absolutely loved science. And when I was in middle school, I had kind of a chemistry lab in my bedroom and loved science and and wanted to go to engineering because engineering really is applied science. Basically, I wanted to do some things that I could see and feel and that would benefit society in a direct way. So really, science and applied science essentially is what I was really excited about. And so at one point in time, I wanted to be an astrophysicist as well and a nuclear engineer as well. But ended up where I am. And if I were to do it again, I'd do it exactly the same way.
So how did you end up in composites? I'm going to make you leap now to your work in Maine. I realized we've been having this conversation as if everybody knows what it is you do, which is not fair to everybody who might be listening. So
Yeah.
I'll say this later too, but I've known you for years now talking about offshore wind and really innovative engineering, design, and build out of offshore wind. You know, the UK has offshore wind, but it's shallow and turbines are bolted to the ground, for lack of a better way to put it. And almost 8 or 9 years now, you've been talking about offshore wind that's floating, which is hugely innovative. So we will definitely get into that. But the composites part is, to me, kind of the secret sauce. So maybe you could explain a little bit about how you got into composites, what composites is, and why you think it's so innovative for what we're doing moving forward in Maine.
Thank you, Kate. And maybe I'll just go back 25 years ago when we get the center started. Maine was shipping its wood away at the time. I was driving by the Maine Portland seaport one day and I saw logs stacked as high as you could and as far as you could. And I asked what was going on here and stopped at the port and somebody told me, well, I don't know. We're just sending our trees to someone else to make something with them and send it back to us. So basically, that was really the wrong thing to do, is take our natural resources and not add value to them in Maine before they leave the state of Maine. So what we wanted to do is figure out ways to use our natural resources where we can actually add value to them in Maine rather than ship the trees out. And that's where composites allow us to do that in many ways. But the center has grown a lot since then, and we do a lot more than just composites that are made out of wood. And so to give you a sense of where we are today, we've grown from 5 people about a quarter century ago that started the research center. We have over 300 people who work here today. And we went from 0 facilities to about 100,000 square foot lab. So we've grown a lot. We have over 100 projects ongoing at the same time right now in a variety of fields. But in 2020, we developed a strategic plan called GEM, and that stands for Green Energy and Materials. So our goal is to bring green energy and materials to the state, to the country, and to the world. And that's essentially where we're heading with a lot of the work that we do. And so we're bringing green energy using offshore wind, for example, to power the state of Maine and power other parts of the country and the world. We're using bio-based materials right now, wood, for example, wood residues and wood waste, to produce the next generation composites that could be used in construction. We use a large-scale 3D printing, for example, right now to help solve the housing crisis in the state of Maine. Maine and throughout the country, as you know, we have a major housing crisis, particularly low-income housing crisis. Maine has over 20,000 low-income homes that are needed now, and really no good plan to get there soon, try to resolve the issue soon, and it costs too much to build them. And we also have a lot of our paper mills have shut down, 5 of them, and a lot of the wood residuals that went from the sawmills to the pulp and paper mills, really, there's no place for them to go now. So we're looking at ways to use these wood residuals now as a feedstock for large 3D printer to print homes. And that would solve a lot of the housing crisis in Maine. But of course, we're not going to overnight solve all these problems. But what we're trying to do is use this residual feedstock, which is renewable and available in Maine, to help use additive manufacturing with 3D printing to print homes. And that would allow us to reduce labor costs, because labor is the big issue in Maine right now. We have an aging population and we can't find enough people to build homes. So if we use large-scale printers, we can reduce our labor costs, but have to educate the next generation of engineers and scientists that can operate these and develop and design them and so forth. So as you see, we're working on a lot of very important societal problems. One of them is housing, one of them is energy, and it's under this GEM initiative, which is Green Energy and Materials Initiative umbrella.
So it's really interesting because I think most people don't think of engineering as directly addressing real-world society problems, which is unfortunate, but understandable, because engineering people get a little freaked out by because it's math and science and all these other technical stuff. But there's a true application there. And one of the things I've always enjoyed is the way that you've addressed policy issues in the sense of seeing what's really impacting the state and trying to figure out how can you use engineering and tools to help with that. It has occurred to me we haven't entirely defined what composites are. If you don't mind just doing that little sliver, that would be really helpful.
Yeah, so composites is bringing a variety of materials together with a binder or adhesive, if you wish, that would allow us to put them together to form new materials. And you can bring in wood fiber, for example, as could be part of composites. You could use resins such as epoxies or vinyl esters or bio-based resins such as PLA. And you can use all kinds of fibers. It could be natural fibers, it could be very exotic nanocellulose fibers that we're working on. It could be exotic carbon fibers or carbon nanotubes and so forth. So composites really is a big family of materials that can be designed from the ground up to solve a particular problem. And so there's a very versatile set of materials. Right behind me here on the video on the screen, you see the Penobscot-Narrows Bridge. The stays that hold up the deck, if you wish, most of them are made out of high-strength steel, but we've replaced some of them with carbon fiber, high-performance carbon fiber tendons, which are quite a bit lighter and do not corrode compared to steel. So that's a composite, for example. Airplanes have composites. For the new jet, the Dreamliner that Boeing has, a lot of composites, which allows it to fly with less fuel, reduces the cost of the fuel for the jet, but also allows us to add more moisture inside because the composites don't corrode like aluminum and metals do. So now when you go to a Dreamliner, it feels a lot more comfortable. You don't dry out, you're not as tired in an airplane because we can put more moisture in because composites don't corrode. So composites can be used on Earth, they can be used in space, and they can be used everywhere in between. They can be made out of bio-based resins or materials. They can be made out of synthetic materials and used in boats, for example. Carbon fiber boats are made out of composites as well.
So 25 years ago, when you saw the logs heading off out of state, were you working in an area that was already wood-based, or were you doing something else?
We started at the time teaching the first wood engineering course at the University of Maine ever taught, and started the work in that area. We were actually building timber bridges at the time because wood existed in Maine, and why go out and buy steel from out of state and so forth. And so, yeah, we've been working quite a bit in that space and got to learn a lot about what the needs are in Maine. And we identified composites as an opportunity to better and more effectively utilize our resources.
So I'm going to make you play a little bit of favorites here, and you can back off and say you don't want to if you don't want to play this game. But in the last 25 years, do you have a couple of projects in particular that you're either super proud of or think have had an impact beyond what you thought they would when you first started it? And when I say you, I know it's not just you. I'm deeply aware. You and I have talked about this at length. It takes a whole team of people. And the Composite Center is a perfect example, in my opinion, of interdisciplinary work. The folks that you have there are not just engineers and scientists. You've got communicators. I hazard a guess you have sociologists, you have policy people. You have a whole team of people looking at stuff. But are there projects that you've been surprised at how they've turned out? You thought maybe it was a throwaway, or maybe you thought it would be something and it was even better?
Absolutely. What I'm most proud of is the over 2,600 students who've interned in our lab over the last 25 years. If I look back and say, what would make me the more proud is the fact that every one of those had a job coming out of this lab, having interned, having been paid to work in this lab, and they've come from over 30 academic departments on campus. So that's really what I'm most proud of, is the ability to use the lab like ours to train so many people that are now successfully in their careers. And then, of course, they've worked on a lot of exciting projects. And if I were to pick one, I would say the bridge in a backpack is an example of a technology that nobody thought was possible. We thought we were going to have to do one day to stop because we couldn't figure out the answer. How do you inflate a bridge, especially, and make it stronger than steel? And that was a lot of tribulations. But it was really a group effort. We had a number of students actually who are on the patents right now with us, who actually came up with some pieces of the puzzle that allowed us to get where we were today. It's that ability to sit down with students that are very young, a lot younger you are, but can think outside the box and really make major change. So there's two other students that that worked with us 15 years ago on this, that without them, there would not be the bridge in the backpack, because they came up with some really amazing ideas. And they went out and tried it out. And guess what? We could actually inflate an arch and bend it out and make it stronger than steel and so forth. But it was the fact that you almost think that you can't do it, but you don't stop. And the key to all of this is not to give up, because the time you give up is the time you lose. And then there was enough excitement to try to find a solution. And students working with us together one-on-one, and they came out of the left field and found some solutions that we never thought about. And here we are today. We've got a business in Maine that's building bridges and shipping them outside the state of Maine, because we didn't give up, because the students got together and we thought about innovative ways. That project just ended up being selected by the American Society of Civil Engineers as the biggest innovation in the world in the field of civil engineering. But again, it was us working together with students that allowed us to get where we are today. So I'm very proud of the students and the staff that really thought through this and got us where we are today.
And just clarify for people who don't know, bridge in a backpack is exactly what it sounds like, with the exception being that the backpack is about the size of a hockey bag, as a nod to Maine's longstanding hockey playing where you can fit composite tubes in there and then pull them out and inflate them and fill them up with concrete. Do I have that right?
Yeah,
And
exactly. Yeah, you can
and
bend it.
span, I don't know that you could span the size of the Penobscot, which is a huge river,
No, this
right?
is, yeah, exactly. These are designed for up to probably 80 or 90-foot spans. Arches, you can put them back to back and go a lot more than that. But basically, you're making an arch that starts in the back.
So we'll include a link to that in the show notes. It is one of the first things that I remember hearing about. And I remember thinking, this is, first of all, so cool that you could put it out that way, but also the innovative use of composites with that. And I think your point about the students is something that I often find people aren't entirely sure what the value is of universities in general. And I think it's not just the fact that students get an opportunity to learn from really amazing people, but I think the converse is true. The people and the faculty who are willing to listen to students can learn a whole lot because students, for better or for worse, are not encumbered by hearing what they can and can't do. So it gives them an opportunity to look at things in a new way and really have some extraordinary innovation.
You're absolutely right, Kate. We have a motto in our lab. You see it in every room. It's called "None of us is as smart as all of us." And that includes, of course, the students and everybody you talk to every day. And because everybody's got great ideas. And really, the key here to innovate in science and engineering is get people a lot of different ideas and respect everyone. And all of a sudden get us to talk. And then spark starts to fly and ideas start to come out. So that's really the process of innovation is really bringing a lot of different people from different disciplines and different ideas together to solve very difficult societal problems. And that's really what excites me every day is the fact that we're trying to solve problems like the energy problem for the state of Maine, the housing problem for the state of Maine. But without having this big team of people, including the students, working together, we can't do that.
So I'm going to make you talk a little bit about the offshore wind project because it is part of what you said with your strategic plan and also because it's what I'm most familiar with. So I enjoy hearing about it and hearing any new updates. So have at it. Like if you don't mind explaining kind of the larger term vision. And I will say unabashedly, Maine has been a leader in this for the better part of 10 years. I think one of the biggest problems I've seen is that people don't realize just how extraordinarily important this is to Maine. And I would argue the world, especially when addressing climate change and rising carbon emissions. And this is a really innovative approach. You spoke at the 2016 Maine Science Festival's 5-Minute Genius. And I remember we limited you to only 5 minutes to explain this. And it was really great. You really cut to the chase and explained the value and the importance of this wind. So I know I said I was going to let you go at it, but that was my relatively brief introduction for you to explain how the offshore wind project you're thinking about is a much larger scale than just the cool turbines we see on a couple of mountaintops in Maine.
Yeah, Kate, and again, it was great to work with you on this project in its formative stages as well. So thank you for your contributions to it. The idea is really very simple. We have a lot of wind off the coast of the United States and the world, the strongest winds typically off the coasts. And to give you a sense of scale, around the US, there's enough offshore wind capacity to power the country 4 times over. And the majority of our population lives in the coastal states. So it makes sense because the energy is there offshore. People are there near shore and connecting the two together. In Maine, we're no different. We've got a tremendous offshore wind resource. The Gulf of Maine has about 156 gigawatts of offshore wind capacity. And to put that in perspective, if we harness just 3% of the offshore wind resource in the Gulf of Maine, we can electrify heating and transportation in Maine. We can all be driving electric cars in the future, and we can all be heating our homes using heat pumps driven by electricity simply by harnessing 3% of the area within 50 miles of the coast of Maine. So we're energy rich, we're just not using that energy right now. And if we did that, we can keep our energy dollars in Maine and we can create thousands of jobs along the way. And what's most important than all of that is climate change and leaving the world a better place for the next generation. That's really what drives us every day here. Climate change, as you know, is an existential crisis for humanity. And offshore wind is a part of the solution. It's not the only solution, but it's an important part of the solution. That's why we're pursuing that. Maine has deep waters off of its coast. And therefore, we can't fix the turbines to the seabed. We have to float them, just like you float a boat. So we've been designing and developing technologies to float turbines that can be placed 20 or 30 miles offshore. You can't see from shore that would harness the strong winds and bring the power back to Maine. And in the long run, our ultimate goal is electrifying heating and transportation in Maine. In Maine, we spend $5 to $6 billion per year on fossil fuels. That money leaves the state of Maine every year. And what if we don't have to use that money to build the infrastructure and the fuel's free? By doing that, then you create a lot of jobs to build the infrastructure and maintain it. You can build boats, you can build ships to maintain it, you can build fabrication facilities, and the fuel's free. So at $5 to $6 billion per year, if you think about the next 50 years, 50 times 5 is $250 billion worth of funds that could stay in Maine. And they could be used to create a whole new industry that allows to create the jobs and stabilize our energy prices over the long run. Because as you know, fossil fuel prices, we have no control over it, regardless of what you hear in the media. The gas prices are not up because of anything anybody did in the US. It's a global market is heading in that direction. So by going to offshore wind, we can stabilize our energy prices and lock them in for the next 20 years, rather than have to be dealing with $4 and $5 a gallon every few years.
I don't know if this will be intimidating to people who hear it or not, but could you give a sense of the scale of the turbines that we're talking about?
The turbines are getting bigger and bigger right now because the cost goes down when you have bigger turbines. Turbines are being designed right now are 20 megawatts. 15 megawatts exist, but for 20 megawatts we're designing. Each blade is bigger than a football field. When you're looking at a 20 megawatt turbine, you're looking at providing enough energy to supply 10,000 homes in the US and probably 15,000 homes in Europe because we're not very energy efficient in the US. So these are very big turbines. And the idea is you fabricate them, you fabricate the hulls in port facilities, you put the tower and turbine on, you tow them out to sea more and beyond the horizon. And that's how you bring the energy back to shore. As I said, Maine is energy rich. Governor Angus King used to say, Maine is Saudi Arabia of wind. Gulf of Maine is Saudi Arabia of wind. But we have a lot of energy in Maine. And then we're working very hard to bring that energy cost effectively back to people in Maine for both environmental and economic reasons.
And is the turbine shaft itself and the blades, is that where a lot of the composites expertise comes in?
Yeah, the blades are all made out of composites. Think about a blade bigger than a football field, right? Without composites, you couldn't build these blades. But we're also designing and developing towers out of composites as well. So the tower itself that holds a turbine that's 350 feet, 160 feet tall, 25 feet in diameter at the base. This big towers could be made out of composites as well. So we could manufacture them locally. For the hull, the floating hull, we're making them out of concrete right now because we have concrete facilities in Maine, but we're researching low carbon concrete that could be used to do that as well. So that's what we're busy doing. We have over 70 patents right now on a technology called Volturnus, the floating wind technology. And we're working not only in Maine, but we're working with developers around the world to implement this technology.
So one of the things that's always struck me, Habib, is that even though you're running this center as the executive director, you still seem to get to do a lot of engineering. Please correct me if I'm wrong, but that seems like you've hit this sweet spot where you get to work with these extraordinary people on interdisciplinary teams, but still keep your hand in the actual technical part. That is unusual, I think, for people who have reached a certain level of kind of running labs and organizations.
Of course, as time progresses, you do less and less number crunching. But what you do is you'll learn a lot over the years. And it's your intuition that allows you to really be able to help people who are younger than you are. So you develop an intuition about things that could and couldn't work. And then we've got some great people now that with the right direction can do some great things. So I think our value becomes more of a direction value to the engineers and scientists. And then we tell them, we think the answer is going to be this, go find it. And they go find the answer because they're so good at it. So that's exciting. It's the ability to give back to young people and point them in the right direction is very satisfying.
I can't think of a whole lot else I want to ask you other than, do you think we will hit a point where the weight of the composites will be the lightest they can be? When I was back in the dark ages there, when I was working with you, the big thing was talking about, I think, 12 megawatt turbines. When you said 20, my head almost exploded. And I'm sure that some of that is because of the advances made in composites. But at some point, we're going to hit a wall, right?
Well, one thing I've learned in engineering and science is no is never an answer. So I think there's always a better way. We just have to find it, right? And that's really what's excites us about engineering and science. There's always a solution. You just have to look hard enough to find it. So I believe we can keep going. And we are developing better materials. We're developing better designs of the blades. One day we could have downwind blades. So instead of being upwind, it faces the wind actually comes in and goes through the tower and back into the blades. And that allows them to deflect more. And not hit the tower and therefore have bigger and bigger turbines. So there's ways you could actually do that. There are actually projects that are looking at turbines in the 50 megawatt range right now. But again, this is all conceptual. But that's the beauty of science. The sky's the limit.
Habib, thank you so much. There's never a time that I talk to you that I don't walk away ever more inspired. You're really seriously one of my favorite people to talk to with engineering, and I love hearing what you're doing. So thank you very much.
Thank you, Kate. So thank you for all the great work you're doing as well. And it's always fun to talk to you. And I love your energy and what you bring to science in the state of Maine and beyond.
Thank you. Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by subscribing on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is hosted by me, Kate Dickerson. This episode was edited and produced by Scott Loiselle. We received financial support from Central Maine Power, production support from Miranda Bouchard, and social media support from Next Media. The Discover Maine theme was composed and performed by Nick Parker.